Hello everyone. Today I'm going to talk about section 3.2, the second derivative and the behavior of the function. According to the first derivative, we have learned how to determine the interval upon which a function increase or decrease by the first derivative. And we can find the relative minimum and relative maximum points if the axis of the function. And I also remind you under here as the first derivative of x, f derivative x greater 0 in a to and b. That's going to give you fx is increasing in a to b. Okay, and in the other case is f's derivative of x less than 0 in a to b. That give me f of x is decreasing in a to b. And lastly, if I have f derivative of c or like x equal to c, right, equals 0, x equal to c, and I have f derivative of c equals 0, then what happened? F of c is relative extrema, which is mean or maximum, right? Okay, so today in this section 3.2, we're gonna try to use the second derivative to determine what happened with the behavior of the fx. So in here, we're gonna have f second derivative or f double prime x here. So the first thing you're gonna have the intervals upon which function is concave upward or downward, and the points of inflection if the axis of the function. So what is inflection? So let me draw it. The inflection point is a point that so you see here in the graph fx, right? And it's have like at first it was concave upward, right? And then after that it's concave downward. So the point that's like a transition point here, that's we call inflection point. Inflection point. Okay, and and similarly with first derivative, but the second derivative, if you have f double prime of x greater than 0 in a to b, that is going to give me f of x, or the original one is concave up. Okay, as you see is bigger here, and in another way, f double prime less than 0 in a to b, then f is concave down. And lastly, if f double prime of c equals 0 in a to b, then f of x may have an inflection point at x equal to c. Okay, so let's move down. Okay, so this concave v point of inflection is all thing that I just told you above about second derivative and the concavity of function. And in here we have one thing is about hypercritical values of a function. So we learned in 3.1 about if I have f derivative of x equals 0 at x equal to c, then you have then you're going to have c is critical value, right? But make sure that c is valid value. okay, or I mean like C is in the domain, in domain, okay. So today in section 3.2, we will talk about if the case that the second derivative of x equals 0 at say at x equal to c again, then c in here is, no, I'm gonna change, I say h, okay. So h is a hypercritical value, okay. And again, h is valid value in domain, okay. So that is a way. Now let's move down here and talk about if we combine the first and the second derivative together, what we're gonna have, okay. So I did talk about a little bit about this in section 2.3 higher order of derivative, and also in 4.2 or 3, I think. But let's come back with this. So increase at an increasing rate is what? What happened with this, right? So look at figure 3a. This is okay as increase at an increasing rate. Why I say that? Okay. So you can see that this figure have a graph as increasing upward, right? Then what does that mean? That means the function is increase at an increasing rate. Okay, so we are having as f the derivative of x is greater than 0, and f second derivative of x is also greater than 0. Okay, so this increasing rate is depend on like the sign of the first derivative multiplied with the sign of the second derivative, and that become the positive. That make the function is increase at an increasing rate. Okay. Now let's move to the second case. We call increase at a decreasing rate. So the function increase if I have f derivative of x is greater than 0. That's no doubt. But for the at a decreasing rate, that means what? That means I have f derivative of x multiplied with f second derivative of x has to be less than 0. So so I have what? I have positive for the first, multiply with a negative for the bottom for the second derivative. That's give me a negative only. Okay, so what does that mean? That's mean the graph is increasing, okay? Increasing, but it's trying to go down later, right? It looks like it's going down later. It's not, the rate is not keep going up like figure 3a. So actually figure 3b here, you can see that the graph is increasing, but it's kind of like going downward, right? So it's gonna increase downward. and this is number 2. And also I call it is increase at decreasing rate. Okay, so that is for number 2. And similarly for 3, we see that is decrease but upward. See that? So that means what? That means the rate is kind of like decreasing, right? So you have the first derivative has to be less than 0. And for the decreasing rate here, which means less than 0, which means the product between the first derivative multiplied with the second derivative has to be less than 0. And I have here as first is negative, then the second has to be also negative, and I have positive here. Oh, wait, sorry. I have to post it here. Okay. And then negative here. So in this case, the second derivative is positive because it's why? Because you see that it's upward here, right? So in this case, f derivative of second derivative has to be greater than 0. Okay. So the last case, decrease at an increasing rate. What does that mean? Okay. So the f derivative x has to be less than 0. But the increasing rate here, that means the product between the first and the second derivative has to be greater than 0. That means what? You are having negative for the first, then you have to multiply with the negative for the second derivative. Then you have the positive. So that means what? Okay. So it looks like the function is decreasing. Okay, but at the increasing rate, because it's keep decreasing lower and lower and lower, right? So so that is a figure 4D here. So here's 4, here's 3, and I call it decrease downward. Okay. So let's do an example. Example 1 here. We have an efficient study conducted on the day shift of manufacturer showed by that the number of units of a product produced by a typical employee 2 hours after 8 a.m. could be modeled by the function. So ft equal to t cubed negative t cubed plus 9t squared, and t has to be from 0 to 8. In the context of this problem, describe the behavior of this function. Okay, so if you see a question say describe the behavior of the function in section 3.1, you just worry about the f derivative of x. And or you can just worry about like the function f(x) is increasing, decreasing, and you're gonna worry about relative maximum and minimum only. But now you are moving to the second derivative of x, so you will learn more. And today you're gonna know the concavity, and it's combined with increasing, decreasing, and the maximum minimum. So so at first step, I have to find the critical value and hypercritical value for this function. Okay, and in order to find critical value, I need to find f derivative of t, which equal to okay, you know how to use a power rule, right? So you put down the 3 So I have like negative, let's put out 3 first, and multiply with a negative 1, and t to power 3 minus 1, which is 2. And then plus with 9, and time with 2. Actually, you should put 2 down first, so you can do 9, 2, it doesn't matter, but yeah, I just want to let you know that 2 ways, okay. And t to power 2 minus 1 is equal to 1. So I don't want to change anything, just say t. And now I'm going to simplify it, and I got like 3 multiplied with negative 1 is negative 3 t to power 2, and then plus with 18t. Okay, so this is gonna be the first derivative of t. And now I need to set, in order to find the critical value, I need to set f dv of t equal to 0, right? So what does that mean? I have that's gonna give me like negative 3t squared plus 18t equal to 0, and I have to think about, can I factor this? And I say I want to factor 3t out. For the first term, I will have t only. Second term, I'm gonna have negative 6, right? Because you factor negative 3, then you have negative 6. And t is gone already, so it's going to equal to 0. And apply for the factor probability, then you have negative 3t equals 0, or t minus 6 equal to 0. And what? And then you will have, maybe I put out here, right? You will have t equal to 0 for the first case, and or the same case gonna be, you add 6 both inside, you're gonna have t equal to 6. And they are both they are both in they are both in the domain of the function fx, no, ft. So let me write out the domain. You should know that the domain has to be t is in between 0 and 8. So t equal 0, t equal 0 and 6 are critical values. Okay, and I have to mark it. Okay, and then now I'm gonna find the hypercritical value, right? In order to find the hypercritical value, I have to find f second derivative of t, right? And in order to find the f second derivative of t, I have to take the derivative of the first derivative, right? So what does that mean? Let me copy this down. And I'm gonna take the derivative of that. And now I'm gonna have what? I have negative 3, no, put down 2, multiply with negative 3, and then t to power 1, 2 minus 1 is 1, plus with 18. T gonna count, okay? That is a constant multiplied with a variable. If that's gonna be just constant. Now you have negative 6 t equal to 18. Oh, wait, plus 18, right? Yeah. And I'm gonna mark this. Okay, so now I'm gonna set f second derivative of t equal to 0. So then that means what? That means negative 6t plus 18 equal to 0. Then what? Then I will have t equal to negative 18 divided by negative 6. Okay. So we equal to what? 3. So I'm gonna just run this. T equal to 3, and it is in domain. I'm gonna just copy this down. In the domain of the function fx, ft, I mean. So t equal to 3 is hypercritical value, right? Okay. Okay. I'm gonna say the here. Okay. Now let me mark this one. Okay, so since we have t equal to 3 is a hypercritical value, and t equal to 0 and 6 the critical values, then you're gonna move to step number 2 here. And step number 2 is put all the critical value and hypercritical values in the number line and make the sign chart. Okay, so let me move down here, and here I did draw ahead already. I'm having right now is a sign chart with for t it starts from 0 to 8. And we have critical value and hypercritical value. I mean, critical value is 0 and 6. For the hypercritical value is 3. I put all them down on the number line here. So now I'm gonna have how many interval? 3 interval, right? So in order to test this interval, I'm gonna have first one. I'm gonna test say number 1. Second one from 3 to 6. I'm gonna test 4, and the last one is 6 to 8. I'm gonna test 8. Test 7. Okay. Now I'm gonna consider about f derivative of t. I know that for the value at t equals 0 here, you know that f derivative of t had to be equal 0. So I can put 0 here. I may gonna okay. And 6 also that the value at t equals 6 also that make f derivative of t equals 0. You can check for the critical value, right? Critical value is 0 and 6 that make f derivative of t equals 0. So I put this f derivative of t equals 0. And for the hypercritical values, when t equals to 3, that make f second derivative of t equals 0. So I put down this equals 0. Okay. Actually, I don't even need to separate this. Okay, so now I will have test the middle. You know what? I just gonna yeah. For the first what should I do? Okay. For the interval, I'm gonna just separate it to make sure. For the interval from 0 to 3, I know that if I plug 1 into the f derivative of t, what I have? f derivative of 1 going to be equal to -3 and 1 square plus 18 times 1, which give me -1 plus 18, which is 15, and that is greater than 0. So I put positive here. I should also have 4 here as a here is also positive. If you want to check at f of 4, that's going to be -3 times 4 square plus 18 times 4. That's going to give me what? I'm going to use my calculator here. So I say -3 times 4 square plus 18 times 4. You're going to have 24, which also greater than 0. So then for the f derivative of 7, you will have -3 7 square plus 18 times 7. That will give me a negative number, but you know, to make sure, I'm gonna have a -3 times 7 square and then plus 18 times 7, and then enter. I have -21, and then 0. That's a negative here, right? And you according to the first derivative in section 3.1, you know that if the f derivative of t is positive, then the ft, the original one, has to be increasing, right? And from 3 to 6 also positive, so then it's keep increasing. Okay. And for the from 6 to 8 here is become negative, so then it's decreasing. Okay. So I know that at here they at here it should be a relative maximum, since it go up and it go down, right? Okay, so what is that value of ft? You know, that's f of at t equals 6, then f of t equal to f6, which give me what is ft? Negative t cubed plus 9, negative of 6 cubed plus 9 times t squared, so 6 squared. That's going to give me, I need to use calculator, so I have negative let's see, 6 power 3 plus 9 times 6 squared. That will give me 108. Okay, so here should be 108. So what does that mean? The relative maximum gonna be at the point 6,108. Okay, and what else? I will have, and now I'm gonna have consider for the second derivative of t. I know that for the first interval I have 1 there, so I have second derivative of 1, which gonna give me -6 times 1 plus 18, which equal to negative 6 plus 18. That's going to be positive of 12. So 12 is greater than 0. So I put positive here. Okay, for the interval from 3 to 6, I choose 4. So the f second derivative of 4 will be equal to negative 6 times 4 plus 18. That's going to be negative 24 plus 18 going to be negative negative 6, which is less than 0. So you have negative here. And last interval, you may check 7, right? F 7 second derivative of 7, which equal to negative 6 times 7 plus 18 equal to let me check negative 6. Times 7 plus 18 that equal to negative 24. We also less than 0. That's 0 here. Okay. Now, if you look back for the second derivative test, what they give us? They give us the a positive of the second derivative will give us the function it become upward. Okay, upward. And I can also draw it like this. Okay. It's up, right? Concave up. And for the negative, it's gonna be down. And then I'm gonna draw it as a down. And then from 6 to 8 is also keep down. So right. Okay, so what happened at t equal to 3 here, right? You should know that if you have function changing from up to upward to concave up to concave down, right? You will have the middle one here, the middle point or the transition point is called inflection, right? Inflection point. So in this case, this is inflection point, okay? As at t equal to 3. So now I to find that point, right? So I have like f of 3 equal to. So I have negative 3 cubed plus 9 times 3 square. That's give me let's see, 3. So that's going to give me 54. So the inflection point in here is 3,54. Okay. So I will now move to the last step. say step. Oh, step. What happened? Step 3. Make a conclusion. All right. So always follow these 3 steps in order to find the behavior. So let me see. Step 3. I want to change this become 12. Okay. Mark this one. Okay. So in order to make a conclusion, I will maybe have to have the table. Okay, so I gonna copy down from copy down a summary table from section 3.1, and now we are talking about interval or the value. So interval, the first value is 0. I don't really care about that. So I'm gonna just start with 0 to 3, with interval from 0 to 3, and the value at 3, I care about that. And what else? 3 to 6, right? And then 6, and 6 to 8, and I don't care about value at 8 because you know, we just care about the increasing and some concavity in these sections. I don't care about this. Okay, done. Okay, now for the interval from 0 to 3, what happened? Take a look at the side chart here. So 0 to 3, I know that is ft is increasing, right? And upward, right? Concave upward, right? So let's say increasing, and I'm going to say behavior actually increasing upward or increasing at an increasing rate. Increasing rate. Why we have that? Yeah, if you check that, you check the first derivative here, f derivative t equals to positive, right? F derivative t is positive, and second derivative t is positive. So then you should the product has to be positive. So I still have increasing rate. Okay, now at 3, what happened? It's not this. At 3, I know that it is an inflection point. Okay, so f derivative x, I don't care about that one. But I care about the second derivative. Okay. Actually, do I need to let me see. I need to have one more. I need to have one more column. So to the right, and this one smaller. Make this one smaller, and then I have to make this one smaller. Okay, this one is hard to make it smaller. So, okay. Move a little bit here. And okay, I can make this one smaller. Okay, so now make it bigger so we can see. Okay, let me call this one as f derivative second degree of x. Okay, so from 0 to 3, I know that is positive, right? And f of x is increasing. Behavior of x has to be increasing at an increasing rate, and interval value at 3. I don't gonna need to care about at 3. No, I don't care. I know that at 3 at the x f second derivative has to be equal to 0. I know this here is to be positive. Okay, so for f in this case is 54, and then I know that's 3 and 54 gonna be the inflection point. Okay. And then now I'm gonna care about 3 and the interval from 3 to 6. What happened? I know that, let's move down here, move up here. I know that from 3 to 6, the first derivative had to be positive. Second is negative, right? First has to be positive. Second is negative. So then f of x had to be increasing. Okay, and the behavior is, we call it increasing at okay, the product between the first and the second derivative is negative, right? Positive times negative is negative. Again, I may can have one more column so you can see clearly. Okay, so I call this is f x multiply with f second derivative of x. Right. And I'm gonna call positive times positive is positive. This is 0. This is negative. Okay. And I have increasing at decreasing rate, because the product between the first and the second derivative is negative, so it's got decreasing rate. Okay, the at value x t equals 6. In here is t, right? I'll change it. T T. Okay, so f equals t equals 0 again. What else? I have f second derivative t is f second derivative t is negative. We don't really care, but yeah, but actually I'm gonna put negative here, and that's the product still 0. ft in this case is f6 is 108, and then I say 6 and 108 is relative say maximum, right? And if I mean, because in this one I don't really care about absolute maximum, but if you want to draw it, you can see it should be the absolute maximum, but I don't want to care about the absolute maximum in this case. Okay, and now for the interval from 6 to 8, I know that's f derivative of t had to be negative, and then the second derivative of t is positive. Oh, no, it's b negative. Let me check again. Yes, negative. Both it's negative. See that? So product has to be positive, right? So then I'm gonna so then the ft has to be decreasing, okay, and the behavior of ft has to say decreasing at an increasing rate, because the product is positive, right? Okay. So that is a way to do problem like determine the behavior of a function in from section 3.2. So you can just the more clear, the better point you have in my class. And now I'm gonna describe more about. I mean, these are the things that you actually just learn from above. There's f of x. If the relationship between the first and the second derivative, that make how it make the rate look like. So you see that the first derivative x greater than 0 and the second derivative x greater than 0, that make increasing at an increasing rate. And you see, like this is like product between the first and the second derivative. Okay, similarly, case number 2, 3, 4 here is gonna explain you more, but I'm gonna just move to example 2 here, and we'll do one more example for you to see what happened, right? Okay. So firstly, I need to state the domain of this function, and because fx is x to power 3/5 minus 1, which is a polynomial function. So in this function, you can say that this is all real number. Okay. So now I'm gonna go ahead and do step 1. Actually, I can copy down some words so I don't have to type too much. Yeah. And okay. I will just clean up this. Okay. Find critical values and hypercritical value first. Okay, so for the f derivative of t x, I mean, what is that equal to? You have to put down 3/5, right? And then you have x power 3/5, and then you minus 4/1. See that? And then now you have minus 0, but you don't either want to write it down, right? So for these, you will have what? Maybe a question here, and then I'm gonna put down like fraction 3/5 x. Okay, now to power 3/5 minus 1, you need to know that 3/5 minus 1 would mean 3/5 minus 5/5, which is give you as power as 3. Let me see. Negative 2/5. So so I'm gonna have here 2/5 negative, right? Okay. So now I have to convert it to be positive power, and let's see what happens, right? I have uh-oh. This should be 3 over 5 times x power 2/5. Okay, now x power 2/5 it's right now it's look like what a fraction, right? So if I say if I want to find the set f du x equals 0. Okay, how can you solve this problem? You're gonna have what? This on equal to 0, right? But then you will have no solution for this case because why? Because in the fraction, you don't gonna have. I mean, you need to just taking care of the top equals 0, but the top in here is 3, so there is no way to make it equal 0. So I can say like no solution for this. So maybe you will think, oh, is there any critical value in here? Actually, there's another thing you may have to consider. If it is a fraction, you have to consider if the bottom equals 0, which is undefined case, right? So you see that f of x is undefined at bottom equals 0. So find x power 2/5 equal to 0. So then in this case, you have x equals to 0. And since x equals 0 is still in the domain. So x equals 0 is the critical value. Okay. Okay, now let's find the hypercritical value. Find the hypercritical values. So in order to find hypercritical value, you need to take the second derivative of x. Which means what? Which means you are taking this guy derivative, right? So, and call that and then review that. So what is that equal to? You're gonna put down say this one. You're gonna put down negative 2/5 up in the front, right? Let me insert equation and then this guy. So put -2. Fancy here. 5. Constancy. And then now x power -2/5 minus 1. Okay, a little bit crazy, but yeah. Now in order to, let me see, let me show it. I want to make it a little space. Okay. So now I'm gonna have what equal to -2/5 times 3/5 will be -6. So let me. -6/5 times x. To power. So -2/5 here. I need to copy this. So -2/5 minus 1 will be equal to -2/5 minus 5/5. That's gonna give me -7/5. Okay. And then I'm gonna still change it to be the positive power. So it's gonna be look like what? Okay. I'm gonna copy it and change it. So this will be -6/5 times x to power 7. 7 here. Okay. And you see now, again, there is no solution if you set f the derivative of x second derivative equals 0. And this one equals 0. And you're gonna say no solution. Because the top is -6. And you cannot make it become 0 if you have fraction. And for the case if f second derivative of x is undefined, at the bottom here, equals 0. So you will have what? You will have, let me see. X equals to 0 again, which is in the domain. So x equal to 0 is the hypercritical value. Okay. Okay, because why? Because either the case if f of x equals 0 has solution, or f second derivative of x is undefined, that will make hypercritical values. Okay, and now I'm done with the first step. So I'm gonna label this. Okay, so we all have only one value for critical value and hypercritical value at the same point, which is actual 0. Now, step 2, we're gonna put these values in the number line and make a side chart, right? So it's gonna be like that. So for this problem, it's maybe easier. So it's go from negative infinity to positive infinity, and the middle one is the critical and hypercritical value at the same point is 0. So now I'm gonna test for t equal to say -1 and 1 here. F first derivative t and f second derivative t and f t. Okay, so the first one, if t equals -1, what happened with f derivative t? I have f derivative of -1 will be 3/5 times -1 to power 2/5, and that will give me a negative value. Oh wait, no, a positive value, because I will check to make sure by calculator. So I have 5 times -1 power 2. Then I have no, that was a wrong way to multiply. 5 multiplied with -1 to power parentheses 2 to power 5. That makes more. Okay, that's make us 5. At the bottom, we have 3/5. So that's supposed to be positive. So I have positive here. And for 1, it's also going to be f derivative of 1 equal to 3/5 times 1 to power 2/5. That also going to be greater than 0. So both of these greater than 0. You can check that, but I'm pretty sure, because why? The top of the power here is 2. That make 1 here become positive. So I have positive here, and at 0, f derivative t and f second derivative t will do not exist. So what about f second derivative t? Okay, so I have f second derivative of 1, -1, I mean. What do I have? I have -6/5 times -1 to power 7/5. Okay, so for the 7/5, okay, now I need to use my calculator. So I have what? -6, I divide by big parentheses 5 times small parentheses -1, close, over, power, over, parentheses 7/5, close parentheses for that, and close parentheses for the fraction, enter, then I have 1.2 with positive. So 0 greater than 0. So I'm going to say here is positive. Now what about f of f second derivative of 1? Okay, so this should be over here, f second derivative of 1. I'm going to have -6 over 5 times 1 over 7 over 5. That will give me negative number because of this -6. Okay, so this is a negative. Then this will be a negative one, negative here. Okay, now for the f of t, I know that the first derivative is positive, then this should be going up, right? And because it is the second derivative is also going positive, so I have this as the upward. So upward. Maybe I change the color. Or maybe I'm gonna just rewrite it as up here. Okay. Concave up or upward. I say concave up. Okay. And then it's keep increasing from 0 to positivity, but concave down. And we will have like a inflection over here. At 0. So I have f of 0 will be equal to what? So go back with the function 0 to 3 foot minus 1, right? So minus 1 will equal to -1. So that should be 0 here, right? So I have inflection point is at 0, 0. Okay? No, 0, -1, sorry. -1, okay? And yeah, lastly, the last step, I'm gonna say step. I'm gonna copy down from here. Okay, step 3, make a conclusion. So I'm gonna have summarize table for the function. So give me 1 second. Okay, so for interval, I should have from negative infinity, search. Yeah, infinity. I don't have infinity here. Check if I have infinity here. I don't have infinity here, so I'm gonna analyze T. Okay. To 0, comma, and then at 0, and the last interval is from 0 to infinity, positive. Okay. So now the row I will just delete it. Okay. I'm gonna say this x, 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 x. And then now for the first interval, okay, let me move up a little bit. You see that the first derivative is positive, second one is positive, product is positive, then you're going to say fx is increasing and behavior has to be increasing at an increasing rate. For the value 0 here, when x equals 0, you should have f of x is do not exist, and if second derivative also do not exist, so the product also do not exist. But for the fx, it is -1, and I say 0, and -1 is an inflection point. And from 0 to positive infinity, for the f(x) positive, but the second derivative x can be negative, so product has to be negative. And I'm gonna say fx is increasing and behavior is increasing at a decreasing rate. Okay, so that's it for this problem, right? Okay, so now I'm gonna just, this one is clean up. Okay, what is this here? Clean this up. Okay, so now let me move to example 3, and we still summarize the behavior of fx equals to x cubed minus 3x squared plus 4. Okay, and at first I will always state the domain, try to state the domain of fx. So domain equal to because this is a function of I mean the polynomial function. So you will have x is always real number, and if you say y is the polynomial function, because you have x power like power something like yeah, the function is become like x power say 1, 2, 3, 4, 5, something like that. It should be a polynomial function. If it become like negative number, no, sorry, like a exponential function or rational function like a quotient, then you have the domain have some restriction. But in here, no, there's no restriction at all. So x is all real number. We'll change this become and now I'm gonna follow 3 steps here. Let's just copy down these 2 steps and changing. Let's see. So first step is always find critical values. Okay, and hypercritical values. I'm gonna delete this. Okay, for the first one. Okay, so f derivative of x will be what? 3x power 2. This will be easy one, right? And minus for 3, no, 3 times 2 is 6, 6x, and 4 becomes 0. So if you set f derivative of x equals 0, you will have 3x squared minus 6x equal to 0. And you have to think right away to the factor properties. And if you factor 3x, you will get first term we're gonna have x, second term gonna be negative 2 and equal to 0. So then you will have solution as say, let me put that here. So I have 3x equal to 0 or x minus 2 equal to 0. So then you have x equal to 0 or x equal to 2 are the critical values. And they are both in domain. So x equal to 0 and 2 are the critical values. Okay. And now for the hypercritical values, I'm gonna take the view of fx. So let me do this. Which mean what? Which mean take the view f the view of x. Okay. Then you will have what? Now I have 6. Now we're gonna have 6x minus 6. Okay, so that's you have set f derivative of set f second derivative of x equals 0. That means 6x minus 6 equals 0, and that will give you x equal to 6 over 6 equal to 1. And it is in the domain. It is in the domain. So x equal to 1 is a hypercritical values, and there's no case that f derivative of x and f second derivative of x undefined, so I don't have to worry about that. Now I will move to step number 2, which is put all the critical values and hypercritical values in the number line and make the side chart. So let me change the color. Here is the number line from where? Net infinity to positive infinity. And I have 0, 1, 2, right? So 0 here, 1 here, and 2 here. Okay, and I have right now I'm having 1, 2, 3, 4 interval. Okay, I will let me make this 1, 2, right? I will test -1. I will test 1/2. I will also test 3/2, and I will test 3. Okay, so now what happened? For f derivative of x. Okay, let me, you know what? I'm gonna have a line here to separate f and t. Okay, and f second derivative t, not t, x. Why I keep with t? This x. And then fx. Okay, so now I'm gonna have separate line. Okay, you know that the 0 and 2 are the critical value. Those make f first derivative had to be equal to 0. So I just put 0 here. And x equal to 1 is a hypercritical value that make the f second derivative of x equal to 0. So put that. Okay, now let's go ahead and test each interval. For f derivative of x, when x equal to -1, so f derivative of 1 we equal to 3. Oh, actually -1. So first interval, right? 3 times -1 square minus 6 times -1. Is that correct? Yeah. And that equal to what? Make smaller. Three times 1 minus plus 6, that can be equal to 9. Greater than 0. So positive here. And I check f second derivative of -1 will give me where that's cx plus 6 -1 minus 6. So it should be -12 with less than 0. Right here. Okay. So for the fx, if you see that f derivative of x positive, so then that's be increasing, and but the second derivative of x is negative, so then it should be downward, right? Concave down. So yeah. Okay. Down. You know what? I actually really like to just have the graph like this better, so that's it can come down from the can come down. Okay. And now I move to the next interval. Actually, now I need to check at f at 0. What happened, right? We know that fx equals x cubed, so f 0, 3 minus 3 times 0 plus 4, that equals 4. So then here is 4. Okay. And now I'm gonna move to the next interval. Say f derivative of 1/2 equal to 3 times 1/2 square minus 6 times 1/2. That's giving me what? Okay, so let me calculate. Okay, so here's my calculator. I'm gonna open it. And now I have 3 times 1/2. I just gonna use 0.5 square, and then minus 6 divided by 2. 6 times 1/2. Also 6 by 2, same things. Gonna be equal to -2.25. So -2.25. 25, which is less than 0. Okay. So that, so less than 0. And And for the f second derivative of 1/2, what happened? I'm going to have 6 times 1/2 minus 6. That means 3 minus 6 equal to negative 3. Also less than 0. Okay, so I put negative here. And then now I'm gonna say for the f of x is because f first derivative of x negative, then fx has to be decreasing. Also, the first derivative is and the second derivative is negative, so then it also has to be has to be concave down, right? And now we're gonna move to the next interval. So I have oh, but before doing that, I will know what happened. Yeah, at 1, we're gonna have 1 over 3 minus 3 times 1 plus 4. So that will be 1 minus 3 equal to 2 plus 4 equals 2. So 2 here. And then now I have from 1 to 2, I'm gonna find the value of 3/2. So let me have f first derivative of 3/2. That's give me 3 times 3/2 square minus 6 times 3/2. That's give me, I'm gonna use my calculator again. So multiplied by 3/2 going to be 1.5, so 1.5 square, and then minus for 6 times 1.5. That will give me negative 2.25 again. So negative 2.25. And I will have another negative here. Okay. But what about the f second derivative of 3/2? We're gonna have 6 times 3/2 minus 6. That's gonna give me, pretty sure it is a positive number, but let's check. 6 times 1.5 minus 6 give me 3. That is positive 1. And I don't care this. Okay, so now from 1 to 2, f derivative of x is negative, so then it's become decreasing for the f of x again. But for the concavity, it's going to be upward because the second derivative is positive. Okay. Now we will check f at f of x equal to 2. So I'm gonna move to the left here. Say f of 2 equal to what? F of 2 equal to 2 over thirds minus 3 to 3 and 2 plus 4. And that's give me 8 minus 6 plus 4 equal to 6. And then I'm going to put a 6 here. Is that correct? No, something was wrong. Let me check. It should be 8 minus. Oh, something was wrong here. Is that? So for the first one, Q minus 2, 4. Let me check. 2 to power 3 minus 6 plus 4. 6. I didn't make a mistake, but oh, I see. I think I need to have square here because the function is 3x squared. Yes, so this is not 6. This becomes 0. Why I know that it's wrong? Because I know that from 0 to 2, the interval is keep decreasing. So I cannot have here at 2, then here at 6. That doesn't make sense. So I have to have 0 here, so it makes sense. Okay. Now I have f2 is equal to 0, and now I'm gonna just go to the next interval for f degree of 3 and see what happened, right? Okay, so let me see. F degree of 3, I know that it is 3 times 3 squared minus 6 times 3. And that's going to give me what? 3 times 9 equals 27 minus 24 gonna be 3. Yeah. And that should be positive. So here's positive. And another one is f second degree of 3. I will have 6 times 3 minus 6. And that's will give me what? 24 minus 6 is 18. We also went 0. Okay, so now I have function has to be fx has to be increasing again, and concavely gonna be upward. Okay. So now I will have summarized table. Actually, I wrote I have down here. Okay. You know what? I'm gonna create another table. So step 3 here. Okay. So the interval is from negative infinity to 0. What is that? 0, 1, 2, right? From negative infinity to 0, and then check at 0. From 0 to 1, and then what? From 0 to 1, and then from 1 to 2. No, for 1 here, and then 1 to 2, and 2 and then 2 to positive infinity. Okay, so now let's take a look at the first derivative. When for the first interval, I have positive, negative, positive for the first derivative, right? And the negative for the second, and the product has to be positive times negative is negative, right? Fx is increasing, and behavior has to be increasing, but at a decreasing, right? Okay, so let's see if I have here. Yeah, same thing, right? Now I have 0 here. What happened with 0? I have f of x equals 0. For the f second derivative of x, I don't know, but I know that should be negative. For the products, it has to be negative. And for the f of x, it has to be 4. And the point 0, 4 is the maximum, relative maximum. Okay, let me see. Yeah, same thing. Okay, so now I'm gonna move to the next interval. So it says 0, 1. I know that from 0 to 1, I have first one is negative. Second derivative is also negative, so I'm gonna put negative, negative, and then product negative, and then this be decreasing, and the last one is behavior. I'm gonna say decreasing at actually it had to be positive here because the product between the negative and negative at an increasing rate. See that? Okay, so at value of 1 here, you know that f of x have to be negative. You don't have to put this value because I don't care that. But for the f second derivative of x, yes, it's 0. And the product has to be 0. This we so 0. Why I forgot that. The fx has to be for 1, you have 2. And I'm gonna say what's that? 1, 2 is the inflection point. See that? Because you have 1, 2 here from 1 at 1 x1 the fx become concave from concave down to concave up after that. Okay, so now I'm gonna move to 1, 2, the interval 1, 2. Okay, 1 to 2. I have 1 to 2. I have negative, and for the first and the second derivative, it has to be positive. So negative, positive, and the product has to be negative. So fx has to be decreasing, and you have to say behavior, right, is decreasing. No, decreasing at a decreasing rate. See that? Okay. And now we're gonna move to f of 2, at x equal to 2, I have f equal x equal to 0 because critical values. I don't care about the f second degree of x, but I know that it should be say positive here, and then this should be 0, and fx has to be f2 equal to 0. And now for 0 and 0, just 0, 0. I'm not sure. Yep. 0, 0. Oh no, not 0, 0. It should be 2, 0, 2 and 0 because the value x is 2. Is what? Go down. You see that is at x equal to 2, fx for the in the left, fx is decreasing and then immediately increasing. Then we call at 2, 0, we have it is a relative minimum. And lastly, from 2 to infinity positive, you will have f x is positive, and f second degree of x is also positive, and product is positive, and then it should be increasing. And I say this behavior of this level has to be increasing at an increasing rate. So okay, and that should be all. Okay, so let me see if I missed anything. No, everything's look good. So just always follow by this summarize table. And now this is a function of fx that we just did, and you see that you see that the function may look like increasing from -2, I mean from -infinity to 0. See that? And then is going down or concave down from 0 to from infinity to 0, and then you have going down, decreasing from 0 to 2, and at 2 it's become like an inflection point for no, actually at 1, at x equal to 1. So it become inflection point. I can show you here, okay? And it changed from concave down to concave up. Okay, so and then after that it's keep going up. Okay. Let's see. I will have this. Okay. I will do this example 4, but I think that most of you now understand already. If you still not understand, you can go ahead and do the assignment. But if you still confused with that, then you can keep take a look at my example 4 here, right? So example 4 here, I gave you the first derivative, I mean the original fx. I gave you the first derivative and the second derivative already. So so let's talk about this, right? So first thing, step 1, find critical value in hypercritical value. And small it, and now you know this stuff. Okay, so like this small line. So now I'm gonna find critical value, and for this, you need to state the domain first, right? Domain. So domain for the fx, you have to remember that because fx is a rational function, so bottom cannot equal 0. So I'm gonna say 3x minus 4 cannot be equal to 0. So we say not equal to 0. So then we have x not equal to 4/3. 4/3, right? So so domain is equal to x that's not equal to x such that x is all real number except 4/3. Okay, and now I'm gonna go down to step 1 here, and I have find critical value. I know that the first derivative is f. Okay. F derivative of x equal to search equation. So this would be what, negative 26, and then 3x minus 4, close that, and 2 here. Okay, so you can using quotient rule to find f derivative of x, but it should be equal to negative 26 over 3x minus 4. Okay. So now I have try to make set f derivative of x equal to 0. Then I have this guy equal to 0. And what do you guess? What is the solution of this? Yes, no solution, right? So because the top cannot, so top is negative 26, constant number. So we still not say no solution. Okay. And now we're gonna consider the bottom if it undefined. So you need to know that f derivative of x is undefined at for at x equal to 4/3. Okay. However, but it is not in the domain of Fx. See that? Because the domain say except 4/3, so it is not in the domain of Fx. So I'm gonna say no critical value. Okay. And another one is f. Now find the hypercritical value. You can have f second degree of x. Okay. Which will be equal to this now. I have 156 equal to 3x minus 4 over 3. Okay. Again, you can still do it by using the quotient rule. Okay. And you will now you will have to set f second derivative of x equal to 0. And what? This guy has to equal to 0. But you're going to say no solution right away. Because fraction with top is constant. And then you have f second derivative of x. You will check another k, which is undefined. And again, x to e is 4/3. But it is not in the domain of x. So no hypercritical value. And now you're gonna move to step 2. But in this step, you may have to have a different little bit with other problems. You don't have critical values, you don't have hypercritical value. So you have to put all the undefined values, critical values, and hypercritical is a number. So in this case, you just have undefined value. That we that's gonna be what? Maybe I have. See if we have enough. I have enough, I think. So I have number line here from net infinity to positive infinity except 4/3, right? So I'm gonna check 0 and I'm gonna check 2. And I have f of x here. You know what? I'm gonna move this down. Okay. And what else? The 2 here. And I have f second derivative of x. And lastly is fx. So a line to separate. Okay. I know that at 4/3 all this become do not exist. So I'm gonna have nobody here in this area. Okay, and it's just gonna check f degree of 0, and let's see what happened. For the f degree of 0, that means what? I have negative 26 over 3 times 0 minus 4 squared. We give me negative on the top, and bottom become positive 60. So gonna be negative 13 over 8, which is less than 0. And then f second degree of 0 will be what? 156 over 3 times 0 minus 4 over third. That's gonna give me 156 over negative 4. So negative 156. No. Oh. Okay, so I have to use calculator for this one. So 156 divided by negative 4. Negative 4. You know what? I have to have penalty. Negative 4 to power 3, right? Because the other term is 0, so I have negative 2.4 something. So negative 0. So I have first one negative, second one is a negative, and fx had to be decreasing and the f second is negative, so then down, concave down. For the other, for f of 2 here, let me be 2, right? You will have negative 26 over 3 times 2 minus 4 and square. So you have what? Negative 26 divided by, so let me use calculator better. So negative 26 divided by, let's see, 6 minus 4, 4, and then square. Then you have negative 6.5. Which is also less than 0. So less than 0. And then f second degree of 2 will give you, I'm gonna move down a little bit. We give you 156 over 3 times 2 minus 4 and cube. That give you 156 divided by 6 minus 4 is 2 power 3 is 8. So 156 divided by 8 divided by 8. That's 19.5. Is greater than 0. So post it here. And then you have going down or decreasing. But for the concave, this has to be concave up. Okay. So we don't want to have like an inflection, do we? Let me see. I have to take a look at the definition of inflection value part. But actually, you know what? Since the fx gonna be undefined and x for third, then no, there's no inflection point in here. It's just like a hole in the changing point. So okay, so now I'm gonna move to step 3. Step 3. Okay, let me actually what and copy out this. I like this better. So yeah. Okay. So we're gonna check the infinity to 4/3, and then 4/3 to positive infinity. At 4/3 actually. 4/3. What happened? And we're gonna delete all this. Uh-oh. Okay, so from negative to 0, and no, 4/3. From 4/3, and then 4/3 to positive infinity. And we'll just delete all the other stuff. Okay, so from negative infinity to 4/3, negative for the first derivative, second negative, and product positive. So this will be decreasing. Decreasing. And behavior has to be say decreasing and increasing, right? Photos have to be, you know, it's just all this. Analysis. And for x have to be denoted also. And behavior is analysis. And for infinity, it should have negative here, but the positive and product has to be negative. So f is decreasing at n and decreasing, right? Okay. So that should be the answer for the conclusion for this problem. Now I'm gonna just delete this. Okay, so according to the table from the text, they also telling us about as y equal to 5 test with I don't care about that, so you don't have to worry about that. So you can see here is a function for this rational fraction. So yeah. So conclusion for the second derivative test, you see that if f second derivative c is greater than 0, then f has a relative minimum at x equals c. So this are another way for testing minimum and maximum by using second derivative. Okay, so So instead of looking for increasing and decreasing immediately for Fx, you can take a look at the just for the f of c's. If it's greater than 0, then f has a relative minimum at equals c. But in this case, you have to know that c is a critical value of f. Then you can apply this second derivative, and you know that if f derivative of c is greater than 0, then it should be like concave up, right? So c is concave up, and you see that as c here, it should be the lowest value. So that's give you the minimum. Conversely, for f second derivative of x is less than 0, that make a concave down. So then the height you see here is maximum. And lastly, for f 0, that actually make an infinite value. It's function. So it's maybe here. It is in fact. So in this case, you know that f second of c is undefined, or f second of c equals 0, then the test failed and cannot be used to obtain information about the relative extrema of f at equals c. Okay, so I think I don't need to go over example 5 here, and I don't have time actually. So I'm gonna stop here. You know what? I will just gonna go over a little bit because this is like using the second derivative test to find the relative maxima. So I'm gonna go over this. Firstly, you need to find the f derivative of x. In this case, you have 3x squared plus 2 and 9 over 2x minus 12. Okay, so then you will have f of x equal to 3x squared plus 9x minus 12. And you set f of x equal to 0, then you have 3x squared plus 9x minus 12 equals 0. And if you divide by 3 both inside, right? You divide by 3 both inside, you will get what? X squared plus 3x minus 4 equals 0. And you factor using the AC method to factor, you have a times c equal to 4, b equal to 3. So two number that's multiple equals to -4, and addition equals 3. What is that going to be? 2 now 4 1. So I would say -1 and 4. So you have x minus 1 multiplied with x plus 4. You have equal 0. Remember that in this case a equal to 1, so you can apply right away. Okay, so I have x equal to 1 or x equal to -4 as the solution for this. And look back the function domain x such that x is belong to all real number. So this is a polynomial. So has to be the critical value. Okay, and I'm gonna have f second derivative of x equal to say 6x plus 9, right? And then apply for the second derivative test. I have to check. I know that I know that we have two critical values, so I have to check f second derivative of 1 will equal to 6 times 1 plus 9 equals 6 plus 9 equals 15 greater than 0. So then you can say that from the second derivative test, you can say that f of 1 will equal to what? Equal to 1 cube plus 9 times 1 square. So let's say f has very, so I would say f has relative, okay, so greater than 0, right? So give up, right? Let's at x equal to 1. And for the other one, it's going to be -4. I'm gonna have what? 6 times 4 plus 9 equal to what? -24 plus 9 equal to -15, which is less than 0. So I'm gonna have go down with the peak. So I have x -4. Okay, so that's just a test, a secondary test for the maximum, relative maximum, and relative minimum. I would like to say we're gonna stop here, and I hope that you will have no problem at all in from the assignments. And I will see you in the next section. Have a good day.